Hey everyone, welcome to the second video for section 3.4. So in this video we're looking at is the more general application of the method of reduction of order. So we saw it in the last video, but in that case it worked out to v double prime equals 0, so what did it actually do? In this video we're going to look at more into what it does in the general case and show an example of how it works and what it does and what it can allow us to do in cases that aren't just constant coefficient and linear equations. Well, it has to be linear, but not constant coefficient. Alright, let's jump on into it. So the point of this video is that reduction of order works in more cases than just what we talked about, and I'll do one example of showing you how it works. So the idea of it is if we know one solution to an ODE, we need to find a second one. A reduction of order gives us a way to find the second one. The idea is it reduces the second order equation down to a first order equation, which we have a lot more direct ways to solve than the second order equations we've been looking at so far. So even if it's not constant coefficient, if we can get from a second order equation down to a first order linear equation, we have explicit solutions and we can easily find them. So the idea here is if we know one solution and want to find a second one, then we can use this method. And the idea is the same as it was before. We look for a y2 of t to be some v of t times y1 of t. We plug it into the equation and see what happens. All right, so let's look at sort of what this method does and how it works. So our general second order linear equation looks like y double prime plus p of t y prime plus q of t y equals 0, because we're dealing with homogeneous problems here. Now let's take derivatives of this y2 and plug it in and see what happens. So y2 prime of t is going to be v prime of t y1 of t plus v of t y1 prime of t. And y2 double prime of t is going to be v double prime y1 plus 2v prime y1 prime plus v of t y double prime 1 of t. And now we're going to plug all of this into our equation. But let me just point out some terms that are going to be important. So this whole thing's linear, right? So I can plug in, basically can plug in the terms one at a time and see what happens. So what happens if I put this term in for y double prime, this term in for y prime, and this guy in for y? Well, they all have just v of t in them, so I can pull the v of t's out the front. What I'm going to see left over is y1 double prime plus p of t y1 prime plus q of t y. But I know that's 0 because y1 solves my equation. So we're going to end up, that term's all going to go away, and all that's left over are terms that involve v prime and v double prime. So I end up with something that looks like a first order equation in v prime, which I can solve by any method and then integrate one more time to get a solution v. Now, the trick with this method is what you get might not be easy to integrate, which is going to cause you problems, but it'll give you a way to actually try to find your solution. So I think the easiest way to sort of do this is just to do an example, and you can look through the book if you want to see the general proof, but I'm going to do one of the examples from the problems in that section about how this works. So the problem I'm going to look at is this one. I have x minus 1 y double prime minus x y prime plus y equals 0, and I know one solution is e to the x. And I want to find a second solution to this. So I'm going to have my y2 of x is going to be v of x times e to the x. So y2 prime is going to be v prime of x e to the x plus v of x e to the x. y2 double prime is going to be v double prime of x e to the x plus 2v prime of x e to the x plus v of x e to the x. And now I want to plug all of this in to my equation. So plugging in y2 into my equation, I get x minus 1 times v double prime of x I get that. So all I did there is I just plugged everything into my equation a term at a time. Now again, I have an e to the x on every term, so I can cancel all of them. Gone, 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 gone. And then I can group all my terms together. So let's group the v double primes, the v primes, and the v's all by themselves. So the v double prime is just multiplied by x minus 1. The v prime is multiplied by a 2x minus 1 minus an x from the second term. And then v of x is multiplied by an x minus 1 for the first part, minus an x plus a 1 equals 0. Now, if I left the e to the x's in here, you would see e to the x, e to the x, e to the x, which is still 0 because we know e to the x solves my original equation, right? I have x minus 1 y double prime is e to the x, minus x e to the x, which is y prime, plus e to the x, which is y. So this term here is 0 because e to the x solves our equation. This comes out to 0. And now I want to see what I actually have when I left this over. I have an x minus 1 v double prime of x plus, this simplifies to an x minus 2 v prime of x equals 0. And now I want to divide by x minus 1 on both sides. V double prime of x plus x minus 2 over x minus 1 v prime of x equals 0. And then I'm going to rewrite this to make this look a little better. V double prime of x plus, this is 1 minus 1 over x minus 1 v prime of x equals 0. And now this is a first order linear equation in v prime. So let's solve it. What is our integrating factor? We have our p of x is 1 minus 1 over x minus 1. So the integral of p of x dx is going to be x minus log of x minus 1. And then my integrating factor mu is e to the p of x. So e to the x minus ln of x minus 1, which is going to be e to the x e to the negative ln of x minus 1, which is going to be 1 over x minus 1 e to the x. Okay, so that's my integrating factor. So I multiply both sides by that. And then the left-hand side, by construction of the integrating factor, turns into 1 over x minus 1 e to the x v prime prime equals 0. So what I did there is I took a shortcut because I know how integrating factors are supposed to work. I took this, I multiplied both sides of this equation by that, and then realized the left-hand side as a product rule. So I get that, and then I can integrate that easily enough to get that 1 over x minus 1 e to the x v prime equals a constant. I'm going to clear everything to the left-hand side, so I get v prime of x equals x minus 1 e to the minus x times a constant. And I want to integrate both sides, and that would normally be integration by parts, but I'm going to cheat a little bit on that to know that this case v of x is a constant x e to the minus x plus a second constant d. Now this is a little bit of cheating here, but if you go backwards, you'll see that when you take derivatives, you get exactly that. Up to a minus sign, I think. But minus signs don't matter here because we're doing constants anyway. So that's my v, which means I get my function y2 of x of the form of v of x, y1 of x. And again, as before, I want to throw out the d because the d gives me a constant which gives me more y1s which I don't care about. I'm going to make the c be 1 just to make things simpler. And so this becomes x e to the minus x times y1, which is e to the x, gives me x as my second solution. And if you look back at the original equation, which I'm going to scroll up to here in a second, you can clearly see that x solves this equation because x double prime is 0, If I put in x prime, I just get 1. So this becomes minus x, and that's a plus x equals 0. So x does solve my equation, and this method led us to that as a second solution to our equation. All right, so there is the general method of reduction of order and how you can use it to find a second solution ODE, assuming you know one of them and you don't know how to find a second one. So you can just do it this way, plug it in, it'll give you an answer because it reduces to a first order linear equation, which we always know how to solve because it's just integrating factors and we get a product rule out of it. All right, so that's it for this one. Thanks a lot for watching. The next one's going to go through 2 examples of solving repeated roots equations for constant coefficients. So we'll go back to the easy case here for constant coefficient equations, and we'll talk about repeated roots examples there. Thanks for watching, and I'll see you in the next one.